All right, so you want to get out that blue packet from the parent graph packet that we worked on last week. And on the third page, I believe it is, we kind of had our general equation that we could use for moving or transforming all of our equations, no matter what parent function. So again, just a quick reminder, we said if there was a number in front of that function that can do one of three things. If it's negative, it would reflect it over the x-axis. If that number is larger than 1, it would vertically stretch it. If the absolute value is between 0 and 1, we vertically compress it. So when we vertically stretch or compress, essentially what we are doing is we're multiplying the y values by that a. So you might want to make a little note here. Multiply y values by the a. We talked about the adding some number at the very end would move it up or down. So if it's a plus at the end, it moves it up. A negative at the end, it moves it down. If you have x minus a number within that function, so whatever the function may be, if it's x minus a number, it moves it to the right. X plus a number moves it to the left. And then we also got into the fact that is if you have some other number in front of that x, a negative number in front of that x, which is in that function though, would flip it over the y-axis. Now, when we do the delta math, some of you may got to it already, some of you may not have. For the c value, it can also do a horizontal stretch or a horizontal compression. So we're going to add that to the c part right here. So I'll just put it down here. So if your absolute value of c is larger than 1, it's what we call a horizontal compression. So horizontally means across, so you'd be taking your function and squeezing it inward. So that's a c inside here, absolute value of c greater than 1. So it's kind of the opposite of the vertical. Okay, when it was greater than 1, it vertically stretched it. But now when our c is greater than 1, it's horizontally compressing it. And then when our absolute value of c is between 0 and 1, then it would be a horizontal stretch. Yeah. Wait a second. So for a horizontal stretch, you can write this down. For a vertical stretch, we multiply the y values. For a horizontal stretch or compression, we're going to divide the x values by the c. So again, the horizontal and vertical are kind of almost totally opposites. Bottom of page 3 in the blue notes. You have to add the part I typed in. You're just writing that down. So if we have, let's just say these three equations, and we'll look at them in a moment. But our parent graph equation is y equals x squared. So again, that just means we're taking all numbers and squaring them for our parent graph table. That's the one that's on the front of your page 1. Negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Now notice this number is inside the parentheses, so that's a C value. If it was outside the parentheses, then it would be an A value, but since it's inside and being squared also, that's our C. So what we just said is we're going to not change our Y values at all. Okay, we said we're going to divide the X values by C. So the Y values don't change, so they're going to stay at 4, 1, 0, 1, and 4. But now our X values are being divided by that C. So normally the X is negative 2. I'm dividing that by 2. So this would be negative 1. So I'd have the point negative 1, 4. Then I have another X value, originally negative 1. I'm dividing that by 2. So negative 1/2 would be our next X value. 0 divided by 2 is still 0. 1 divided by 2 is 1/2. And then 2 divided by 2 is 1. So that's what that would look like. And I can pull that up over here. So there's our parent function. And if I put 2x squared in here, it looks like we took our parabola and squeezed it inward, or it's actually like the same as a vertical stretch as well. Okay, because if I squared each one inside, when the 2 is inside the parentheses, it's really the same as 4x squared, which is the same as a vertical stretch. So that's why it's kind of can be a little tricky. And so again, if you kind of look at this point on the original one, that point is at 1, 1. I took that x value divided by 2, so it's 1/2 1 right there. Right there. All right, and then the other one would be is if we, other examples, if we have 1/2 x squared, 1/2 quantity x squared, again, we're not changing the y values at all. So they're going to stay as 4, 1, 0, 1, and 4. But I'm taking my x values from my original table and dividing them by 1/2. So dividing by 1/2 is the same as doing what? Multiplying by 2, okay? So this would be negative 2 divided by half, or negative 2 times 2, which would be negative 4. Negative 1 divided by a half would be the same as negative 1 times 2, so that would be negative 2. 0 times anything is 0. 1 divided by a half, or 1 times 2 is 2. And then 2 divided by a half is the same as 2 times 2, which would be positive 4. And if we take a look at that, over here, this actually is going to look like a horizontal stretch. So we took the black parabola and pulled it outwards horizontally. It also looks like a vertical compression, okay? Because if I squared 1/2, I have 1/4 as of the a value now. Okay. All right. So that's that. So just as you go on the delta math that you're going to finish, there were some questions on like that, and that can be a little confusing. The other thing I want you to do, well, there was a Desmos that was also assigned to you today. So if you want to pull that up, or you can just look up here for right now. Slide 1 tells you what you're going to be doing. It says from left to right, so it's going to be incorporating piecewise functions with the parent graphs. Okay, so we did piecewise functions like earlier this chapter, and we're going to incorporate with the parent graphs. So you always start on the left, work left to right. You're going to identify that parent equation, parent function, and then figure out which way it's transformed. The way you restrict do the piecewise on Desmos, like that if part, is you have to use these curly brackets. Okay, and I'll show you where you find them in a moment. So if you look at slide 2 here, you see a whole bunch of graphs. There's like a green one here, then a red one, then a purple, and then a whatever, light blue. I don't know. So you have to try and create that whole thing because that's a piecewise. It's all one graph, but it's made up of 4 separate graphs. So you start on the left, like we said. So when I start on the left, I see I'm going up on the green and then down. So which parent function is that green one? It's part of what? Absolute value. It looks like a part of a v. So right away, I can go ahead and say, all right, this is going to be absolute value. All right, it's flipped upside down. So I'm going to put the negative in front. And I know that it is moved left 3 and up 2. So within my absolute value, I'm going to go plus 3 because I want to move it left. And I'm going up 2. So outside would be a plus 2. Now, if you notice, yeah, it matches, but this graph goes on forever, and our original one had to stop at 2. So the way we do that is with the piecewise functions and inequalities. So instead of writing an if on Desmos, we don't write if. We press the curly brackets, which is next to the p. So if you press shift and then the button next to the p, you get that curly brackets, and then we write that inequality. So this parabola, or sorry, this absolute value, if you scroll over, it goes to the left forever. So I would type in negative infinity. So to do that, you press negative and then just spell out infinity. Is less than x. And then we wanted to stop at negative 2, and it was a closed dot at negative 2. So I'm going to write less than or equal to. So I do the less than symbol, and then you can also just press the equal button on your computer, and it makes it less than or equal to. And we needed to stop at 2, or sorry, negative 2. So I put negative 2, and notice now that stopped there. So we're good to go. Then I would go to my next one, which will be a cubic, and so forth. Okay?